I think now we're ready to begin our presentation, so I will turn it over to the engineering team.
Welcome to this webinar from our MPS Now Lab. My name is Xavier Rivas. I'm here with my colleague Francesca Estragués. We are both applications engineers in MPS Barcelona office. And now we're going to explain how to design MPS. We're going to explain how to cover the concurrent requirements in ADAS designs with the MPQ8875A. Online, there is Amir Ranjwar and Cecilia Yuen, that are two field applications engineers in the US. Here in this slide, you can find their contacts, and if you have any doubt or you need any kind of support, do not hesitate to contact them. Now, once the presentations are done, let's start with the presentation, with the webinar. As it has been said, the goal of this webinar is to present an MPS solution to solve the concurrent requirements in ADAS designs. In order to clearly achieve this goal, firstly, we're going to review the main requirements of ADAS designs and the meaning of concurrent. Then, as a kind of state of the art, we will present the previous solution that was released by MPS aimed to solve concurrent issue, what we will know as the previous reference design. However, as it will be seen later, this previous solution presents some limitations that, as it will be seen later, will be solved by the backboost topology. This topology and this solution will be explained at last sections of this webinar. The end of the presentation will be focused on showing in real time how this last solution works. Then, once the agenda for today has been covered, we will turn to the Q&A. So now, let's start with introduction. As it's known, the Advanced Driver Assistance Systems, also known as ADAS, are of highly interest in today's automotive market. Nowadays, the number of sensors and cameras that are placed into this kind of designs is increasing a lot in order to monitor every single part of the car. As a consequence, there is also an increase on the power demand of ADAS. On the other hand, each sensor inside these systems have their own specific input voltage requirement that can be around, for example, in cameras of 10 volts. This is, the battery voltage must be down converted to different voltage levels to supply the required power to all the system. Due to that, the ADAS designs must ensure the following aspects. First, the efficiency must be reduced in order to reduce also the power loss. Second, must occupy the minimum amount of the area, these designs. And thirdly, many safety relevant functions must be able to operate during start-stop event. In other words, this means that there are some functionalities that must ensure its operation during all the time the car is in use. This last requirement brings us to the problem that we will try to solve today, the so-called cold run. The cold run is a known enemy for automotive designers that appears when starting the engine. At this moment, the car battery, as it can be seen in these two figures, falls to a low value for a short period of time and then rises slightly again. From these figures, we can observe that when the motor is cold, so in the state of cold run, the voltage decreases until 3.2 volts. As it has been said in previous slides, some ADAS must ensure their functionality along all the time the car is in use. Then, the system must be immune to this car battery profile and supply a constant voltage level for common ADAS systems. In order to solve this issue, MPS has released a reference design aimed to keep the output voltage of the power stage at a constant level, regardless the input voltage. All the documentation about this design can be found into the link that is presented here. As a general overview, this reference design consists on adding a boost converter between the input of the system, that is usually the car battery, and the common step-down converter that is seen in any automotive designs. This boost converter will convert the battery voltage during cold run in order to acquire a stable voltage level. Apart from this pre-boost will act also as an NME filter, so the obtained ME noise will be low. The main limitation of this design is that at high output voltages, we get low amount of available power, making this design not suitable for ADAS applications. In order to overcome this limitation, we have used the buck-boost topology. This kind of converters contains 4 switches that, depending on their state, 3 different modes of operation can be obtained. The first mode of operation is the buck mode. In this mode, the Q1 and Q2 are switching, and Q3 is open and Q4 is closed. Then we will obtain the buck converter, and the output voltage will be lower than the input voltage. At this mode of operation, we obtain high efficiency. The second mode of operation is the boost mode. In this case, Q1 is closed, Q2 is open, and Q3 and Q4 are switching. Then we obtain a boost converter, and the output voltage will be higher than the input voltage. Finally, we can also obtain a buck boost mode. In this mode, the output voltage is more or less the same as the input voltage, and the 4 switches are commuting. In this mode of operation, is the not recommended one because we obtain high noise. To clearly see what happens during cold run, in this slide is presented how the converter will theoretically work. Assuming an output voltage of 5 volts, at the beginning of the profile, when the input voltage is around the battery voltage of the car and starts to decrease, the converter will work in buck mode. Is seen in red. Then there will be a short period of time where the 2 remaining switches will start to commute, and the buck boost will start to operate in buck boost mode. Finally, when the battery voltage reaches its minimum, around 3.2 volts, the converter will work in boost mode. Then, when the voltage of the battery rises, we'll enter to buck boost mode, and finally, we will go to the buck mode. Apart from the kind of topology to be used in ADAS designs, it's also important to select the better IC to cover all the requirements. It has been said that the power demand with high output voltages is a must. Then, the proposal done in this webinar is to use the MPQ8875A. This 4-switch synchronous buck boost converter, thought to be used in sensor fusion systems or camera monitor systems, is able to work in a wide input voltage range, from 2.2 volts to 36 volts, delivering up to 5 amperes of continuous current. Other 2 important characteristics of this IC is the protection features, such as the overcurrent protection, the short circuit protection, or the input and output over voltage protections, and the I2C interface with 2 pages of OTP memory. This I2C interface lets the designer to increase its flexibility on the design and also to reduce the need of external components. For example, in common converters, the soft start is configured by adding an external capacitor. In this case, it's done by IC, letting the designer to avoid one capacitor and also to increase its flexibility to change this parameter whenever they want. It's important also to say that it has OTP memory, so the device can be configured 2 times in order to, when the device is switched on, the configuration will be saved. At this stage of the webinar, we have presented the problem that is to overcome the cold run rate issue for ADAS applications, where the output power demand is high, while the output voltage required is also high. We have also presented the best option to overcome the problem, that is, using a 4-switch synchronous buck boost converter. And we also have presented the best candidate to be used, the MPQ8875A. Now it's time to present the main tips to design this IC in order to get a stable voltage during cold run. Firstly, we need to take into account that when the input voltage decreases up to 3.2 volts, as the output power must remain the same, the current to the inductor will increase. Then, the selected inductor must have a saturation current higher than the maximum current that will pass through it. This maximum current can be calculated by adding the maximum input current under cold run conditions and the inductor ripple current. As it can be seen in this oscilloscope capture, by applying a cold run profile at the input, seen in yellow, we obtain constant output voltage fixed at 10.5 volts in green. In orange is plotted the current that passed through the inductor. And as it has been explained in the last slide, a peak of 9 18 amperes is obtained when the input voltage reaches its minimum. It can be observed in this square in red how this peak happens when the input voltage it reaches its minimum. For this reason, the selected inductor must have a saturation current higher than this maximum value. Secondly, the IC must be configured taking into account this current peak. And for this reason, we must disable the overcurrent protection. This protection feature has a maximum limit of 9 amperes. And as it has been said, as it has been seen before, the obtained current peak is above this limit. For this reason, if it's not disabled, the IC will shut down and the output voltage will not be constant. On the other side, at normal input mode, the allowed input voltage range goes from 4.5 volts to 36 volts. In order to cover the full range of the cold crank profile, it's needed to set the low input mode, which allows voltages until the 2.2 volts. All these configurations can easily be set with the graphic user interface of the chip. As it can be seen in this slide, the GUI has 2 pages with a huge number of available configurations, such as the compensation network, here, the current limit, the protection features, or the back boost thresholds. We must change the input voltage placed in the first configuration, in the first page of the configuration of the GUI, here, and the OCP mode, that is the overcurrent protection mode, here, and change it to non-response. Last but not least, it's important also to take into account the efficiency of the system, depending on the input voltage. As it can be seen in this plot, the efficiency changes notably depending on the converter operation mode. During back boost mode, the efficiency decreases. Then, depending on the application, it's needed to change the back boost thresholds to work as much as possible into the back mode, where the efficiency is higher. This means to reduce the range where the IC works in back boost mode. By applying these design tips, we are able now to measure and get important conclusions about the performance of the MPQ8875A. Firstly, it's shown the maximum output current depending on the output voltage when a cold crank profile is applied at the input of the IC. As it can be observed, the maximum current decreases when the output voltage increases. Here, for example, with an output voltage of 3.3 volts, we obtain a maximum output current of 4.3 amperes. Then, if we increase this output voltage until, for example, 10 volts, where most cameras operates, we obtain that the maximum output current has decreased until the 2.1 amperes. This analysis has been done by plotting the output voltage and getting the load current where the output voltage does not show any change. If the output current overpasses this limit, the IC does not shut down directly. As it can be seen in this slide, when the current is higher than the allowed, in this case, for example, 2.5 amperes, the output voltage, that is shown in green, decreases until the point where the IC can supply the maximum power. So it will decrease until 1.25 volts. Other important measure is the one that shows the maximum output current with a fixed output voltage of 10 volts when the minimum input voltage of the cold crank profile is changed along the range from 2.5 volts to 7 volts. When the minimum input voltage is around 2.5 volts, the maximum output current obtained is 1.5 amperes. Then, if we change this minimum voltage of the cold crank profile to, for example, 6 volts, we obtain that the maximum output current has increased until 4.4 amperes. And as a conclusion, with the MPQ8875A, we can get high level of available power at low input voltage levels, making this solution a good candidate to be used in ADAS designs. Moreover, as it's only used a single chip, that most of the configurations can be set with the I2C interface, the number of required components is reduced, and consequently, the area is also reduced. An example of this reference design that will be soon released by MPS is this, the power state for sensor fusion applications. In this reference design, the MPQ8875A is used in order to supply a constant voltage to some cameras where the required input voltage is around 12 or 10 volts and other loads. Now we will pass to make a real-life demonstration. Firstly, as it can be seen here, we have mounted the evaluation board of the MPQ8875A with all the wires connected to the oscilloscope and the power supply. Here we can see in the oscilloscope that in yellow we have the input voltage that is always doing a Cochran profile. In green, we can see the output voltage that it's constant to 10.5 volts. As it can be seen, we have obtained a stable voltage, so the back-boost converter is working as it's expected. In orange, here is showed the switch node of the first switch node, and shows how when it's switching, the converter is working in back mode. Is working in back mode. Finally, in blue, we have plotted the current that passed through the inductor. If my colleague now increases the load until 2.3 amperes, it can be seen how firstly the output voltage has decreased in this time where the minimum input voltage is happened. That is when it's 3.2 volts, and also we can see how the current through the inductor has increased. This peak has increased. So now, if you have any question, we can.
Thanks, guys. As we mentioned at the top of the session, if you mouse over your Zoom webinar interface, you'll see a QA button, and you can click there and type in any question that you might have of the presentation. Just another reminder as we're waiting for anyone to type in a question, the webinar will be available for on-demand play at monolithicpower.com/webinars. Look for that next week. All right, I am not seeing any questions coming in. So we must have been so thorough in our presentation that there weren't any questions remaining. But thank you for your time today. We appreciate you joining us and look forward to interacting in the future. Bye now.